Hello everyone, I'm Group 33 and Steven Peng Xingguo.
I'm Lu Xinlin.
I'm Sun Jianing. In our project, we're going to be looking at how we apply BERT to the task of question answering. And we will introduce it in the following four aspects. First, I would like to introduce the algorithm that we use. This is the transformer neutral network architecture that we initially created to solve the problem of language translation. The transformer consists of two key components, the encoder and the decoder. The encoder learns what is English, what is grammar, what is context. If we stack the encoder, we get BERT, a bidirectional encoder representation from transformers, which under the hood is a stack of transformer encoders. The training of BERT is done in two phases. First, we pre-train BERT to understand English, and then we fine-tune BERT to learn specific tasks. The goal of pre-training is to make the model learn the ability to represent features with generality, which helps fine-tuning quickly improve performance. Let's look into the picture. The left figure is pre-training procedure for BERT, and the input is an obscure sentence. The right one is fine-tuning on the question answering problem. We pre-train BERT with masked language model and the next sentence prediction. C is the binary output for the next sentence prediction, and the T's here are word vectors that correspond to the outputs for the masked language model problem. On the fine-tuning phase, if we wanted to perform question answering, we would train the model by modifying the inputs and the output layer.
Our task is given a question and a passage of text containing the answer. BERT needs to highlight the span of text corresponding to the correct answer, which means predicting the beginning and ending token of the answer in the text. So every training and test sample of the dataset consists of a reference passage and a question. How do we actually apply BERT to the question answering? We are going to give it a question. Who helped Beyonce overcome her depression during the years following the Destiny's Child split? And the reference text we will use is given in the slide. The answer that we are looking for is her mother. So that we will do is we will take all the tokens from the question and the reference text and pack them together in the input. It starts with the CLS token, and the SEP token is to separate the sentence. How BERT is able to distinguish the question from the reference text in addition to this SEP token. We have these things called segment embeddings. To highlight the answer, we have is to start token classifier. These are the tokens from the reference text, and then for every embedding, we are going to multiply the final embedding by this vector that I've labeled the start. It's the weight of the start token classifier. We will apply the softmax activation function on the output. What that gives us is the probability distribution. If it's working properly, it will predict the highest probability for the token her. It does the same thing for the end token. It will predict mother as the end of the answer span.
Let's look into the details of the model that we implement, the decides of major orders of magnitude, and the device precise specifications are shown in the following tables. Since the main memory and GPU memory on our system are both limited, we can only extract a portion of the SODA version to decide, and the GPU is used for machine learning training and validation. Meanwhile, the CPU is used for data preparation. The left figure is our model architecture, and the right figure is an input example in the BERT. We choose this dual BERT for Q&A problem solving. First, our objective is to extract the important news from the context, not automatically generate the answers. So an encoder is required for word embeddings and feature extraction, but a decoder is not necessary. Furthermore, because lightweighted distilled BERT can perform well by distilling BERT base and tackle the challenges of hardware devices and resource provision limits. We did evaluate tests for performance between before and after fine-tuning. The reason for fine-tuning is that the pre-trained model cannot fully meet the requirement of the task. After our hard work, we made that the loss of the model reached about 0.2 after 3 epochs of fine-tuning, and accuracy reached over 60%. Generally, we achieved a great performance improvement. For further course, we deployed this dual BERT to the Amazon, and the crowd deployment confirmed that we can guarantee the model robustness. Our main contributions are listed below. Due to the time limited, please refer to our final report for further more information. Thank you.